Hi everyone. So we only have 2 labs left in the semester, and right now we're going to talk about the nickel complexes, the nickel complex salt. We're going to talk about the synthesis and analysis. Now, I say that we only have 2 labs left in the semester. On paper, this one is broken into several parts. It's broken into the synthesis, then analysis of how much ethylene diamine that we have, then analysis of how much water we have, then analysis of how much nickel we have. So on paper, it's 4 different labs, but I'm collecting it as one lab report. So I'm going to treat it in this lecture as though it's all the same. Now, nickel complexes. Well, when we have let's say we have a carbon atom, right? And we imagine it starting out with 4 electrons, and that it can hold up to 8 electrons in its valence shell. So it can hold, these 2 then become a bond, another hydrogen brings its own electron, another hydrogen brings its own electron, another hydrogen brings its own electron. So we end up with a maximum of 4 bonds there. This is accurate for the nonmetals, but for metals, it's a little bit more complicated. And for the metals, in order to really understand it, we need to talk about Lewis acids and bases. So what we've talked about before was Bronsted-Lowry acids and bases. So in the Bronsted acids and bases, the focus was on the H plus there we go. H plus that gets given from one to the other. So you've got gaseous hydrogen chloride and water into liquid form. Then they collide, and one of the lone pairs on the water can go and grab the H, and that gives us a chloride ion and the protonated water, aka hydronium. aka hydronium ion. So here, what we're focusing on is the hydrogen going from point A to point B. But there's a different way to look at this reaction. And that different way to look at the reaction, so Bronsted acids and bases focus on the H+. The other way to look at it is that in order to have a bond between this H+ and that oxygen, what we need to have a pair of electrons. We need to have a pair of electrons for the 2 to fight over, because remember, a chemical bond is atomic nuclei having a tug of war over electrons. So the other way to look at it is to focus instead on the electrons that are involved in forming that bond. So Lewis acids and bases focus on the electrons, and usually on the electron lone pair. Now, what do I mean by this? Well, here's what I mean by this. If you have water molecules, and they're just kind of, by themselves, there's a very, very low chance that they will, split each other apart, and you'll get a hydronium and a hydroxide. But that doesn't usually happen. But suppose you add to it something like this. Aluminum trichloride. Now, the aluminum trichloride doesn't have any hydrogens on it, so it isn't a Bronsted acid. But when it reacts with the water, it generates, these water molecules first come in and replace the chlorides, and then, because they're not stable on their own like that, they end up losing because they're not stable on their own like that, they end up giving away some H pluses. So we have something that we can add to water and we can generate H plus. But this molecule right here is not an actual this is not an actual Bronsted acid because it isn't donating protons to anything. What it does do, however, is that it accepts electrons from the water molecules, and those electrons become the ones that form the bonds. So this is a Lewis acid. And since this is a Lewis acid that accepts a pair of electrons, and these water molecules are donating those electrons, the water is a Lewis base. Now, water can be considered, it is an acid and it is a base. It is a Bronsted acid and base. It is a Lewis acid and base. It is very weak in every case. And a lot of the time there is overlap between the Lewis acids and the Bronsted acids. A lot of the time there's overlap between the Lewis bases and the Bronsted bases. In this case, hydrogen chloride is definitely a Bronsted acid, but you could also look at it as the hydrogen here is accepting a lone pair. Therefore, the hydrogen chloride you could look at as a Lewis acid also. And the reason that this distinction exists is because there are a lot of things that are Lewis acids that are not Bronsted acids. So, prime example right here. But another example is almost any ion that is made from a transition metal that dissolves in anything. So transition metal cations are Lewis acids. And what this means for us is that they form bonds with Lewis bases. But one of the things to remember about, where's my, is that it? Yes. But one of the things to remember here is that these sorts of bonds are different from covalent bonds, and they're also different from just electrostatic attraction. So electrostatic attraction, like, prime example, potassium chloride in a salt, this attraction is not really directional. They all have, you happen to have positive charges and negative charges, and they glom together. The attraction, though, between the Lewis acids and Lewis bases is very highly directional. Let's go back to the example of the aluminum chloride. And yes, I know that aluminum is not a transition metal. I just want to use an example of what I mean by directional. So if you take aluminum chloride and you dissolve it in something like diethyl ether, the bond that forms between these will form between the oxygen and the aluminum using the lone pair that's on the oxygen. And then all of these bonds will take up positions in a tetrahedral arrangement, in more or less tetrahedral arrangement. This particular bond is particularly weak, so it's not going to move the others as much, but it's going to be more or less tetrahedral. It's going to be more or less tetrahedral, so that this bond has some covalent character. And we can think about it by it, I mean this bond, of course. We can think about it as a very weak covalent bond. Where it is nowhere near as strong as a bond between an oxygen and a carbon. It's nowhere near as strong as this bond, for example. But it is still very strong. It's not just that the molecule happens to be around. And if we look at, now this is a situation where we have, actually this would be positively charged, negatively charged, and that charge, those formal charges also make it a lot weaker. But the thing is, this is between the oxygen and the aluminum when the aluminum starts out as neutral. If we look at the transition metals, then when the transition metals dissolve in, let's say, for example, water, we end up with something that has a much stronger positive charge. And so we end up with something with a much stronger positive charge. And as a result of that, the bonds that are formed between it and water molecules is much stronger than in the aluminum complex. Now, I keep referring to this as a complex instead of a molecule. And that's because, as I said, these bonds are pretty weak. In fact, they're weak enough that if you happen to have another molecule around that can form a stronger bond, 1, 2, 3, 4, 5, 6, that if you happen to have a molecule around that can form a stronger bond, let's say, for example, you have carbon monoxide, what you get happening is that the carbon monoxide can just replace one of these water molecules at room temperature. And so because these these structures are weak enough that the pieces that are made from nonmetals can come and go as more and stronger binding molecules appear, we don't refer to it as a molecule. Instead, we call it a complex. Yeah, so instead we call it a complex. We could also call it a complex ion. If the whole thing is uncharged. Oh, by the by, carbon monoxide is the strongest ligand that only binds through one bond. There's a lot of reasons for that. There's back bonding that happens, but the reason I bring this up is that this is also the reason why carbon monoxide is very, very toxic, and why you don't want to run your car in the garage for very long. The carbon monoxide will bind to the things in your cells that oxygen gas is supposed to bind to, because it's the same size and it is way too strong. Yeah, so anyway, we refer to these as complexes, or if they're charged, we refer to them as complex ions. And these pieces down here as ligands, or if you go into biology, they pronounce it ligands, because that's just how they do it. Now, nickel, so specifically nickel 2 has 6 places for ligands to bind. Now, I didn't say that nickel 2 has 6 ligands on it. In this case, it does, but it doesn't necessarily have to. Case in point, if you add a ligand that is very strong at binding, not because of a ton of back bonding, but rather because it has 2 places that can bond to it, then that can also replace water molecules as ligands. And because it has 2 places that it can bond, there are 2, we call it a bidentate ligand. So there's the monodentate, bidentate and tridentate. There are lots of examples of bidentate and tridentate ligands, but what we're going to be using for the purpose of our class are ethylene diamine. So this part down here, this is the ethylene, and then these two, these are NH2 groups. So that, and we've got two of them, so they're diamines. Now, since ethylene diamines can bind in two different locations, and there are 6 possibilities here, ethylene diamines, we can get more than one ethylene diamine bonded to each nickel ion. We can get them bonding like this, we can get a couple bonding like that, and then one more like that. And as a result, there are lots of different ways to run this reaction. And as a result, there are multiple different possible complexes that we can get out of having the ethylene diamine and the nickel 2 in solution at the same time. Now, since this is an ion, it therefore has a charge. This has a charge of 2 plus. And so let's just take this and replace it with water again. Now, when we have this complex, the way we get it out of solution is that we turn it into a crystal. So it needs to crystallize. But in order to crystallize, there has to be some sort of ion to go along with it. Because if it's just this by itself, then the fact that it's positively charged means that complexes would push each other apart. Let's use this one. The counter ion we're going to use is sulfate. And so what we're going to end up with is a salt that is made from a complex nickel ion and sulfate. And because these don't fit together really terribly well, there's also going to be some number of water molecules in there's also going to be some number of water molecules that are in the complex, that are in the crystal with it. These extra water molecules right here, these extra water molecules are what we call waters of hydration. They are not ligands bound to the nickel. They are water molecules that are basically filling in the gaps between the gaps that would otherwise be in the crystal if it was just the pure complex and the sulfate. So what we're going to do, what I've already done and made the video of, and you're going to watch the video, and you're going to watch the videos of, and imagine that you're doing it because, coronavirus, and we don't want to have a whole bunch of people die. What we're going to do is we're going to synthesize this using 2 different methods. Now, this might not be the actual complex that we get, depending upon which method we use. The procedures are available online on Canvas. I expect you to look at those procedures themselves. But essentially, we're going to start out with nickel 2 sulfate. So 4 hexahydrate. We're going to dissolve it in water. Actually, we're going to dissolve it in sulfuric acid, but let's just pretend that it's just water. And we're going to add the C to H, what is that, 8? Yeah, 8. N2. We're going to add the ethylene diamine. Ethylene diamine from here on out is going to be abbreviated as EN because I don't want to have to write out the whole thing every time. We're going to add that, and we're going to end up with a substance that has the formula nickel En, then some coefficient, some subscript for the En, for how many we have in the complex. The other spaces for ligands are going to be filled in with water molecules. And here, we have a maximum of 6 places for ligands minus 2x, because every one of the ethylene diamine takes up 2 spaces. So every one of these is going to kick off 2 of these. And then, of course, the counter ion SO4 and some number of waters of hydration. Now, there are 2 main places in which the synthesis differs between our 2 methods. The salt made using method A is going to have a concentration of En that's roughly the same as the concentration of nickel during the reaction. Salt B has a concentration of ethylene diamine that is in large excess versus the concentration of nickel during the reaction. That's the first difference between the 2. So that basically the difference in the formula is going to be the difference in the value of x. How many of these you have, and for every one of these you have, you lose 2 of those. The other difference is kind of a consequence of this. Because salt A is going to end up with more water molecules as ligands, salt A is going to be harder to crystallize. Because water does a really good of being dissolved in water. And as we've already discussed, what determines if something is good at being dissolved in water is whether or not it can interact with the hydrogen bond complex, with the hydrogen bonds that water likes to form. ethylene diamine can interact with those. It can donate hydrogens from the hydrogens on its on its amine groups, the hydrogens that are attached to the nitrogen, aka the hydrogens on the amine groups. Those can donate to hydrogen bonds, and it can donate the electron lone pairs to the hydrogen bonds. However, if these lone pairs are used up by binding to the metal, then it's harder for water to get at the hydrogens. Also, they're already used up, and it's this part instead that's pointing out towards the water. Carbons and hydrogens attached to carbons generally don't contribute to hydrogen bonding, and especially not in water. So salt B, with a much higher ethylene diamine concentration, is going to have more ethylene diamine ligands and is therefore going to be less soluble. So that means that this is really easy to crystallize. Whereas the salt formed using method A has fewer ethylene diamines, and therefore it has water molecules pointing their hydrogens out. So it's much more soluble in water, and therefore harder to crystallize. Okay. So these are the two basic differences between the salts made using the different methods. Now let's talk about the analysis. What we've got here, so our analysis is going to be, first of all, the yield of the reaction, and secondly, we're going to want to know what are the values of each of these. There. We're going to want to know what are the values of each of these. So let me just write it up here. We've got nickel, we've got ethylene diamine, we've got water, 6 minus X, we've got sulfates, and we've got Y there, the waters of hydration. So our analysis is going to focus on figuring out what this formula is. And the way we're going to go about it is we're going to figure out the percent by mass of each component. So for the nickel, we know that there's only one in every complex. But if we find out the percent by mass of nickel in a given mass of the entire salt, then we know how many moles of this complex we have in that salt. So this is actually really important to figure out. And this is something that we're going to do using absorbance spectroscopy and applying Beer's law. The second one, the the ethylene diamine, this is something where we can use the reactivity of the ethylene diamine to our advantage. So ethylene diamine is a Lewis base, but it's also a Bronsted base. So that means that we can use acid-base titration to figure out how much of this we have. Now here, for the sulfate, we don't actually need to specifically figure out how much sulfate we have. And the reason why is because the sulfate is here as a counterion. So we have exactly 1 mole of sulfate for every 1 mole of nickel. So once we know how much nickel we have in a sample, we can calculate how many moles that is and just figure that sulfate has the same number of moles. And then finally, for the waters of hydration, now this y here is a coefficient. It's just like the x. The x is standing in for a whole number that goes there. The x is standing in for a whole number that goes there. The y is standing in for a different whole number that goes there. So for the waters of hydration, figuring them out is fairly simple. We just mass a sample of the complex salt before and after heating it. Now, when I say that we mass it before and after heating it, this is actually pretty important. The waters that are present as ligands, the metal ligand bond has covalent character. It's not typically considered like a full-on covalent bond, but it is a bond, and it is a hell of a lot, and it is a lot stronger than water molecules that just happen to be sitting around filling in gaps in the crystal structure like the waters of hydration. So what we're going to be doing with that one is we're going to be heating it at 90 degrees C in order to drive them off. Because at that point, because 90 degrees C is hot enough to force the waters of hydration to leave without actually removing any waters that are present as ligands. So, how do we go about each of these? Well, let's start with let us start with the earliest one in the schedule, the acid-base titration.